So up until this point, we've talked about processes primarily in isolation. They're not quite in isolation, I suppose, because we have one process creating another, but we don't have the situation where processes are really working together. And that really is kind of a valuable thing to look at. So that's what we're going to talk about in this section, interprocess communication. So, right, so far I had this idea of kind of independence, right? Processes kind of working alone, right? The alternative, right, is this idea of cooperative processes. So I may have processes that somehow, share data, right? So maybe the one process computes something and then passes that data to something else, right? So that's what you call kind of cooperative. So there are a few reasons we want to do this, right? And these are coming from the textbook, and some of them I would agree with, some of them I don't really agree with, but we'll walk through all of them because they are at least comprehensive. So first one right there is basically information sharing, right? So you can maybe think of that in terms of, you have two programs running, right? Maybe they're from different vendors, and there is some sort of integration, right? So maybe you can think of, maybe like, for example, you think of your web browser, right? So something like, Chrome has maybe a main process for the browser, and then if you have certain plugins, right? It used to be maybe I want to use Flash as an example, but Flash is now integrated in Chrome, so it's not such a good example. Maybe actually let's jump to Firefox. Imagine Firefox, right? Firefox is one program that's running, right? It's one process that's running. Then also, right, running inside of that, right, is another process, which is basically the Flash process, right, for doing things like running Flash video, right, displaying stuff. Those are two processes that are somehow working together, right, and they have to share some information, right. What URL are we at, right? That's kind of some information needs to be kind of shared between those two things. So that's one thing you could do, right, is you'd have kind of some idea of programs integrating, right, and sharing information. Second thing we have there, right, is computation speed up, and this to me is kind of the most valuable. So basically, what we're saying there is that I can make things faster. So if you think about, for example, a video encoder, right? In a video encoder, a lot of times what will happen is they'll have kind of a multi-thread model, right, or multi-processor model. And what that is basically saying, I'm going to have one process that encodes this part of video, another process that encodes this part, another part that encodes this part, another part that encodes this part, and so on and so forth, right? The idea there somehow, right, is that if I can break up my work into individual pieces, then those individual pieces, right, I can send them to different processes, and those processes maybe can live on different CPUs, and that means they'll all be able to run in parallel, right? And if they'll run in parallel, I get to basically do a larger amount of work all at the same time, right? So hopefully I get some speed up from running those things in parallel, and that really is a very big advantage. The third thing I have here, right, is modularity. So here, I guess we can jump back to the kind of the web browser kind of example, right? So it's like, well, I have different tabs open. All those maybe could be a different process, right? Because if they were a different process, that means that if one fails, the other ones still stay up, right? So I make kind of my system more modular. And you can maybe think about that as being kind of an any sort of IDE that has multiple things open. So maybe you have like a game editor and you have multiple scenes open, right? Each of those maybe could be in a different process, just because again, right, if there's an issue in one of them, right, maybe it'll kind of stay contained in that module, right? It'll only fail there. And also, right, you get kind of the performance benefits as well. The last thing here is convenience. And this is the one I don't really like. Really, to me, convenience somehow is tying in with the rest of them, right? So information sharing is somehow convenient, right? It's convenient that my two programs work together, right? It's convenient that my programs run faster. It's convenient that my program, only part of it will fail at a time, right? Those to me are all kind of convenience, together. So that's my opinion, right? Obviously, right, other people have differing thoughts there, but I think convenience is really rolled into the three above it. So point is here, right, is that having processes that can kind of work together is very, very useful. So previously, right, in another section, right, of the textbook at least, we kind of discussed some overall methods for doing IPC, right, so inter-process communication. And those are basically shared memory and message passing. So as a quick refresher, right, shared memory means that basically I have this one pool of memory, right, so I have this thing here, just kind of pretend that's a square, and we have, process 1, process 2, right? And basically each of these can go and it has basically direct access into this memory, right? So there's some number here, right? So I have, a magic number here, right? Process 1 can read that, process 2 can read that, right? One of them can write it, the other one can read it, right? Basically it's some kind of shared area, right, where both processes kind of are equals, right? And they can do whatever they want in there, right? That's the idea of shared memory. The other idea is message passing. So message passing, if I were to diagram, maybe looks more like this. I'll draw a little bit more carefully now. So P1, P2, right, a little lifeline to represent that they're kind of running at the same time. And P1 sends a message to P2, right? So it does a send, right? And so it basically is sending something, a specific message just to that P2, right? Maybe P2 sends a message back. And so on, right? I have these kind of discrete little packets of information that are flowing back and forth. So I have my two overall choices, right? Do I want them to work together in a shared area, or do I want them to pass messages back and forth? I can do either of those. So here's some questions though, so we can think about a little bit. So let's just read this from the slides. Are there times when one method in particular, right, is necessary, right? So is there a time when I really need to have message passing over shared memory? So maybe, maybe, but it's a little bit odd. In general, if you can do one, right, you can do the other. Both of them, right, they're both going to be ways, right, basically to communicate between different processes, right? So that's fine. Where we maybe have issues, right, is, for example, in shared memory, maybe you aren't able to make the allocation that you want, right? Maybe your system's really strapped for memory, so it's like, well, I can't really afford a shared spot in addition to whatever the processes have, right? Or maybe you may also have implementations in that, like maybe there's only certain things that are supported on your system, right? And then actually a big one is basically in terms of kind of like a hardware setup. So if you are maybe doing some sort of network configuration, maybe it's more natural to use message passing, right? Unless you have special hardware that lets you do shared memory, right? You're kind of constrained if you're doing it over a network, right? So things are a little bit different there. But overall, right, they really are solving the same problem. So, all right, the second question here, right, is which is faster in terms of system calls? So again, just think about this for 1 second, and then we'll talk through it. So here, right. Well, the faster one is going to be message passing. The fastest one is going to be shared memory, right? So shared memory, basically P1 and P2 can just go and do whatever they want. So it's like you can picture you're in C, you basically just have pointers to this one array, and both of your processors can see that same array. Now, if you do that, there's not really an overhead if you're manipulating, right? If you're reading from it or writing from it, it's just kind of a variable for both programs, and that's really great from a performance standpoint. The issue, though, with the slowdown we get, right, if we're doing the other method, right, if we're doing kind of message passing, is that, oh, hey, every time I want to do a send, I need to go to the OS and do a message send request. When I do a message send request, that's basically calling a system, right? You're invoking a system call, right? It's going to take time, right? And usually the receiving processor has to make a call too. Basically, what that means is you're going to pay the penalty, right, of having to run two system calls, right? System call send and system call receive, right? And that's a whole lot more, right, than just going in and saying, oh, there's a variable that's, there's a pointer somewhere in memory that I can do stuff at, right? That has no overhead in terms of system calls, versus, message passing definitely has, this overhead. So our faster one, right, is going to be obviously, right, our shared memory, right? So this is fast, and this is slow. Maybe really quick about the downsides. So message passing is kind of a little bit more safer than shared memory because everything's kind of just in these little chunks that get sent around, right? When I have shared memory, basically there's the issue of, oh, two processes maybe are competing at the same time to write something, and it's like, well, who's going to get the value there written at the end of the day, right? I may kind of have issues keeping kind of this value here in sync, right? That may be a problem, right? So shared memory tends to be a little bit less stable just because you have two things kind of competing with one another, right? Versus message passing, you're just passing along these kind of discrete pieces, and they can't really go missing per se, right? They're kind of from one to another, right? If the message does go missing, you just resend it, right? But there's no way kind of to tinker with the message, right? It's kind of all encapsulated really nice. So it is kind of more stable. So let's do a quick conceptual example of what shared memory systems might look like. Now here what we're going to be doing is working on kind of an archetypal problem in kind of process communication. And that is called the producer-consumer problem, right? This thing here. So producer-consumer is basically saying the following. I have two processes. I have a producer and I have a consumer. The producer creates some sort of an object, right? Something that, some product, right? And then the consumer, consumes that product, right? I guess it's a pretty easy there coming from the name of it, right? Is I have basically things being created and things being consumed. Now you can maybe think of this as kind of modeling all sorts of problems, right? You can maybe think of this as being, one example, maybe some sort of server system, right? So maybe the client does something like request, oh, I want a web page rendered that has this and this and this, right? Then the server computes some stuff, right, and passes it out, right? Maybe that's some example there that you could have, right? You can think of it basically as any system that maybe is somehow making requests, right, or servicing requests, right, or dealing with stuff, right? They'll all kind of look like producer-consumer, right? So it's a very kind of common problem, right, of just of a process creating something and then another process consuming it. So what we want to do basically is talk through different ways to solve this. And actually, we're doing it here, right? We'll also do it in other sections of the course as well, because this is kind of a very simple problem, right? Or a very archetypal problem. So this is what we're doing right here, right? Producer-consumer. So first, we're going to start here by basically solving it using shared memory and see basically what happens. So on the right-hand side, I have code. I'm going to go through this. One thing to keep in mind, right, is this little more warning up here, right? This is conceptual, right? I'm going to use stuff that's not really, in an API, right? It's just, me needing to show you guys stuff. So don't expect this is, C code you can write and it'll compile. It won't really work that way. Okay, so I have basically 3 different regions in my program here that I can look at. And let me actually just divide that up real quick. So I'll draw on some margins here. So I have kind of my first part, this is so shared, producer, consumer. I'll highlight the stuff that's already there. So I have 3 little fragments of code there. I try to space them out a little bit, but hopefully the lines help a little bit in knowing what goes where. So first of all, right, I have basically my shared data. So this is going to be basically stuff that's available to everybody, right? So the idea of the shared memory model, right, is to say that both processes can access the same stuff. So what is it that I can access? First 2 things are basically going to be kind of compiler time things. The first is a defined buffer size, right? So that's kind of me declaring a constant to say, okay, this is how big the buffer is, right? Because there is somehow this idea, right, is that maybe if I have my producer working faster than my consumer, I might have a pool of things that it's created, right? It's not necessarily going to be producer creates one thing and then passes it to consumer, consumer consumes it, producer produces another one and then passes it to the consumer. I may not be in that situation. That may happen, but that's not really, we can do a little bit better than that, right? If the producer is running really fast, right, we want to basically have a buffer to store all the different things that the producer has produced, and then the consumer, as the consumer works through things, right, just grabs something that is available. And I'll do some drawing in a second to show you guys the model. So anyway, the point is, right, we have kind of a buffer behind the scenes to store products that are kind of need to be consumed. Then what we have, right, is we're going to use this over here called item. Item is a struct. I'm not going to bother to fill it in. What it is representing the data type that the producer is producing and the consumer is consuming. Okay, so now we have over here kind of the more important stuff, right, which is basically my array. All right, so my array is basically my buffer, right? So this is where my data is going to be stored. So you just picture this, right, as being kind of a standard buffer. I know I didn't draw in the right number of spaces, but that's fine. Somehow, right, the idea is that I produce things here, right? So inside of here, right, I'll have, A, B, C, right? So maybe these are 3 different things I've created at runtime, right? My producer goes and adds these, right? So when my producer creates things, right, what happens is it basically adds to this array here, right? So it adds, a D over there, right, or an E over here. It does that, right? So producer, right, is kind of adding things over there, right? And this is going to be basically represented by a in variable, right? So when I build new things, right, I'll add them into the queue, into the array. I don't want to use queue here. I have to be careful. I'll add them into the buffer, right, in this particular position. The other thing, right, is that I have basically this out variable, and so this out variable is basically going to be pointing me to, where do I take things out of? Actually, my arrow should be a little bit over here. I should be pointing at A. That's basically where I'm taking things out of the array from, right? So I'll have these 2 pointers, right? So I have my array, right? I have 2 indices / pointers right into it to show where do I add things, where I take out things, right? So that's what I have, right? So my buffer variable is this over here, right? This array, and I have obviously my out and my in variables annotated on top of that. So that's my shared variable. That's the data that basically on both sides are going to be using. All right, so over here, right, we have basically the producer first, right? So the producer is going to basically go and say, okay, I'm going to have basically what this is called this is a busy loop, right? This is busy waiting. So this while loop here is basically meant to make the producer wait around until there's a space for it to do stuff, right? Actually, so just to back up for a second, right? So we are talking to the shared data, right? But then what the idea is, I have 2 processes running, right? I have that producer and the consumer running, right? And they both have different pieces of code, right? So the consumer is running this stuff over here, the producer is running this stuff over here, right? So that's great. And we're actually going to now talk through, right, the code that the producer is running. So this is one process that's running, right? It's using that global stuff. So inside of that, right, basically I have that first loop here, right? This is basically an infinite loop, right? Because the producer is just going to keep on building stuff, forever. Inside there, I have another loop, right? And this loop looks a little bit funny, right? Because this is the one I said was a busy waiting loop. Notice that there's a semicolon right after that while loop. And so that loop there, what we need to do, what it's doing, right, is basically it's waiting for, is there a space for me to add something or not, right? Because if there's not, right, then how do I produce something new, right? I need to basically wait around. And so you can see it's basically, what it's doing, right, is it's basically checking to see, is there overlap between that in and the out variable, right? Are those, overlapping or not, right? Is there a spare space for me to act on or not? And so it's going to sit there and it's going to wait basically until I get to the point where it's like, yeah, there is a space available for you. So let's say there's a space available for you. Then what we do, right, is we basically add the new thing we produced to the buffer, right? So that's what this line here is doing, right? Our next produce goes into the buffer at the in position, right? So I've added, my E or whatever I have to my array. And then, right, I need to update I, right? So I equals I plus 1 modulus of buffer size, right? Basically, that's me on top, right, moving my arrow, basically to the right. So it's like as I add things, right, I need to move it to a new index. And I'll do that over and over and over again. I can go like that. That's kind of more accurate there. So I'm kind of making space, right, for whatever is going to be the next thing, right? And the modulus there is basically to do a wraparound, right? So at a certain point, right, I filled it up, right, I may need to go around to here, right? That's what my modulus is doing. So I kind of have my circular, it's acting like a circular queue a little bit, right? So it's like if I've gotten to the end, right, I can just circle around back. And so this will run forever, right? It'll just keep on adding things in front whenever there's a spare space. The other bit of code I have here is for the consumer. So the consumer is some of it's similar, right? I have, of course, the infinite loop up top, so that means I'm just going to consume things forever. Then over here, I have my while loop here, right? And this, again, is the special type of while loop where I have the colon directly at the end, so it just is kind of some busy waiting stuff. And what that really is doing is checking to see, is there something available or not, right? Is it empty or not? So if it is empty, then I can't do anything, right? There's nothing for me to consume, right? So I'll check to see whether those two arrows are kind of equal, right? If they are equal, then implies that there's nothing there. Okay, next line, right, next consumed, right, so I would basically take something out of the buffer, and that item I take out of the buffer, I save it into a variable, right, and then I can, consume it, right, so there is some sort of code here that would happen, right, to consume whatever it is I took out. But once I've taken things out, right, that's when I basically update my out variable, right, so my out variable basically needs to move forward, right, so it's like out here, right, so once I've used up A, I basically need to step forward, right, and be like, okay, now I'm pointing at B because I've already dealt with A, right, so I'm gradually consuming from the end. So there we have it. So that's kind of a shared memory solution basically to the problem, right? This producer-consumer problem, right? So we're adding things at one end, removing things from the other end, right? You have two processes kind of running at the same time. Now, one question to ask yourself here is just a little bit at the end, which is, does this code seem safe or not? So this is maybe a little bit hard for you guys to answer, but just to give you guys a heads up, right? So basically where we have issues is over here. So let's see. So look at producer for a second. And producer, let me try changing the ink color here. Success. So here, notice, right, we have basically this line over here, right? It has my while loop, right? I notice that I compare in with out, right? So out is over here. Oh, I guess I didn't change my ink color after all. Let me try that again. Is that success? There, that's success. So now we're cool. So we have there out, right? Out is basically circled in green, right? But notice that out is being changed over here, right? So I'm comparing out from producer, right? But then I'm also doing it basically over here, right? With my consumer is where I'm changing it, right? And this somehow gets to be a little bit of an issue, right? When I have two things running in parallel and they're both using the same variable, right? That ends up being an issue. Same thing happens over here, right? In that where I'm changing in over here and then I use in over here, right? This is an issue as well. The issue right, that comes up there, and we'll talk about this a lot more in process synchronization, is things maybe go kind of out of whack. So what may happen, right, is I basically checked it. So you can imagine two processes running in parallel, right? Maybe one process, goes to read the variable, right? It reads the contents, and then quickly, right, the other process kind of steps in and does an increment really quick, right? It raises that variable kind of after I've read it in the first one, but I haven't actually compared it and acted on it, right? So if I kind of change things behind the scenes, right, then there's an issue, right? So it's here you can imagine, right, is that in the first loop, right, I compare with out, right? So maybe I read out, and I'm about to evaluate that true or that equality symbol there, but all of a sudden over in consumer, right, I increment out. Well, if that happens, right, then all of a sudden the value that's really an out is not the value that the producer read and is using to compare with that other stuff, right? It's using to compare with this. Those two things will kind of be out of whack. So if that happens, right, then there's going to be an issue, right? Where basically there's kind of inconsistent state because because two people basically are reading the same variable and one of them's changing it, and that, right, is going to be an issue. Again, right, we'll talk about this a whole lot more once we get to process synchronization. Okay, so moving along. Okay, so next up, right, is of course message passing, right? So it's a little bit different, right? We talked through shared memory. How does message passing look? So message passing, right, you're going to basically have these two kind of functions just all the time, send and receive, right? Because I need some way to send a message, I need some way to receive a message. And I just have kind of this one argument here to say, okay, there's a message that's going in and out. So question there in slides is, and this is for you guys to think about for a second, how much does it matter if a message size is fixed or variable length? So think about that for a second. Well, so at the end of the day, it really doesn't matter, right? So if it's, if it's variable length, that's nice, right? I can transmit whatever I want. If it's fixed length, all that means is I need to basically divide up how long my message is and send that basically as a header, right? So I could have a header that basically says, okay, you're going to be this long, right? And transmit that kind of ahead of time. That's one thing that I could basically do, right? And if I do that, right, if I kind of build a way to send my size across, right, then the recipient knows how many times, right, to do to receive, right, and so basically it's like, well, then I can send anything of any length that I want, right. So basically, I create a variable length system from one that's fixed length. So that's something that's easily kind of addressed. Okay, so some kind of direct, some nomenclature here, right. First of all, right, when we say that two processes communicate, right, P1 and P2, we'll say that it's a communication link. Now that is kind of a term from our textbook. I don't know how widely people really use that, but we'll stick to it just because the text uses it. So that's a communication link. The other kind of terms we want to introduce is basically the idea of direct communication versus indirect communication. So direct communication is basically saying, okay, I have process P1 and process P2, and those processes directly talk to one another, right? P1 sends a message to P2, right? Process to process. Versus indirect means over something like a mailbox, right? So there may be some sort of a buffer in my system where it's like, well, I send a message to that mailbox, and then the other process reads from that mailbox, right? So there's kind of an intermediate. So maybe just a quick diagram here. So direct communication looks like this, right? So I have maybe P1 and P2 running side by side, P1, P2, right? And they just kind of pass the message across directly, right? Goes back and forth. Versus for a mailbox system, right, I have maybe my my process, right, is going to talk to some big bin, right, my mailbox system, right, and then the other one kind of reads from that, right? So I have kind of an intermediate there. So that's kind of the difference between my direct communication, right? So this is direct, the bottom one is indirect, right? So I have two different approaches, and they do different things, right? So the top one, right, direct communication, I typically have these two commands here, right? I have my send command, my receive command. The first one there called symmetric is basically saying, okay, if I want to send a message, I need to know where it's going to be sent to, and if I want to receive a message, I need to know where it's coming from. So that's symmetric, right? Both the sender and the recipient, right? Both of them need to know basically who's on the other side of that communications channel, right? Where is it going? Where is it coming from? We'll call that symmetric. The other way to do this, right, is basically asymmetric communication, where I have my send and my receive, and my send looks the same, right? I'm sending to a process, but on the receiver's end, they don't really know where the message is coming from, right? So over here, I have this ampersand of ID, basically say, oh, hey, when I do a receive, I'll receive a message from anybody, and then I'll just write down where it came from, right? So I'm not really saying that I need to get a message just from this one process. Instead, what I'm saying is, get it from anywhere, and then I'll store the value of the PID of the process that sent it in that ID variable, right? So I'll get it from anywhere and then just write down where it came from. So that's going to be asymmetric, right? So I have those two choices. Below, right, I have indirect again, right? So indirect is kind of a little bit different. A lot of times what happens, right, is you basically just do a send, right, to a mailbox, right? So I have my send here to mailbox, receive on a mailbox. And so mailbox, right, I've kind of drawn it here, right? This is my M over here, right? This is one big mailbox. And everybody kind of just deals with that, instead of dealing with individual processes, they just go to that mailbox. Now this is a little bit interesting, right, because I can also have situations like this, right? I can have a P3 over here, and maybe P3 also reads from that one mailbox, right? So a mailbox represents something that I can have multiple people adding stuff to and multiple people reading stuff from, right? So it gives me a little bit more flexibility. One issue though is that if I, basically send a message to a mailbox, right, and I have multiple people reading from it, who gets that message, right? So I have here, say P1 drops off a message in M, right? P2 is monitoring it for receives, P3 is monitoring it for receives. What do I do then? Usually what happens is I have to have some sort of conflict resolution system, right? So I need to have basically some way to say, okay, you know what? P2 has priority for receiving messages over P3, and so I'll let P2 basically get that message first, right? That's what I'll have to have some system like that, right? Or maybe if I want to, I can do some sort of a duplication thing, right? So I can have a many-to-one relationship, right? Where it's like, well, I get a message to M, and that means that M basically gives, or broadcasts it, to everybody else, out there. It makes copies of it. So I can do either approach, but it's something that basically I need to think about for a little bit. Moving along, the next aspect of message passing systems is this notion of blocking versus non-blocking. You guys maybe have already heard that term. Also, you made the analogous term, right, is also this synchronous and asynchronous, right? So these are really kind of attributes, or they're behavioral attributes of kind of the send and receive functions, right? So I can have what is called, for example, a blocking send versus a non-blocking send, or a blocking receive versus a non-blocking receive, right? I can have kind of these four combinations here. So what does that mean? Well, I have kind of the diagram on the right with an analogy there, right? So blocking is, for example, you imagine you're on a phone, you're calling somebody. If you're calling somebody, right, you're basically going to be, there, waiting for them to pick up, right? You're not going to, move ahead and do something else, right? You're kind of active on this, right? It's blocking you from moving forward, right? You have to complete your call before you can go and do anything else on your phone, right? So that's the idea of kind of blocking, right? I want to send a message, right? And I'm going to wait until that's, it's sent before I move forward, right? That's blocking, right? Or also synchronous. The other version, right, is really this non-blocking, right? So non-blocking says, oh, you know what, I'm just going to send a message and it's just going to go out there, right? I'm not going to block on that send. I'm just going to proceed down and do my other stuff, right? I'm not going to wait around. So here you can see it's a little bit like texting, right? So you send a text message, it just goes, right? You don't have to wait for the person to receive it, right? You just press enter and it's out there, right? So that's non-blocking, right, or asynchronous. And so we have these overall choices, right? So when our sender receives, right, when we run them, do we want them to be blocking? Meaning, do we want basically the program to sit there until it's confirmed that that thing is completed its task, right? Completed its send to receive, or do we want to do non-blocking? Meaning, just send it, just try to receive it, right, and then move along, instantly afterwards, right, without waiting for anything, kind of to confirm what happened. Right, so I have kind of my choices there. I can do blocking versus non-blocking. Now, this is kind of a nice, a feature, right? And it actually gives us a little bit of power. So one thing to think about really quick, right, is this producer-consumer problem, right? So one question here for you guys to think about is there any way for me to easily solve the producer-consumer problem, given that I have my choice between, given that I want to use message passing and that I have my choice between blocking and non-blocking. So think about that for 1 second. Is there a way I can easily solve that problem using this? Okay, so on the next slide, I do have kind of some little solution here, right? So this is my solution using the kind of the sends, right? And this is using basically blocking commands, right? So this is very simple. All we're saying is, okay, hey, you know what, in the producer, when you create something, do a blocking send, right? So go to the consumer and say, hey, I have this available. On the consumer's end, do a blocking receive, right? So wait until I get that next item, right, and then act upon it, right? So it's basically a handoff thing, right? The producer is basically creates something, right, holds on to it until the consumer wants it, right, gives it to the consumer acts on it, right? And then it happens just again and again and again and again and again, right? So it's very, very easy there to solve that producer-consumer problem. The only issue, right, is that here I've lost my sense of buffer, right? So in the previous example we had a buffer where it's like, well, if the producer produces things at a faster rate than the consumer, then it can still, it can still do work, right? It can still fill up that buffer and then the consumer gets to it when it gets to it. But here, right, basically we're saying is we do this one at a time, right? So one at a time, which maybe is a little bit slower, but it is definitely going to be much more stable. Right? We aren't going to have any of the issues we had with the shared memory, where it's like, well, these two variables might go out of sync. So last thing to talk about here, right, is basically this idea of the buffer capacity. And we have three choices, right? So here, this is basically a zero capacity buffer, right? So we're limited our production rate matches our consumption rate exactly, which is maybe not an ideal thing, right? If they kind of go at different rates. So that's a little bit bad. The other thing we talked about on the previous slide is basically unbounded capacity, right, which is where we create an array of size 10. We say, okay, I'm going to allow 10 products to be created, right? That's fine. The last option, which we haven't seen here, maybe we'll talk about later, is unbounded capacity. Basically say, okay, you know what? I'm going to basically create as many things as I can, right? Maybe I'll send like a linked list and I'll just kind of queue them all up, right? And I'll act on them as I can. So I have those choices. All right, so we've been through shared memory, we've been through message passing, right? Hopefully you guys have now kind of a better idea, right, of how these things work, as well as a little bit of the conceptual syntax that's required to use them.